Assalamu alaikum. Welcome to the new lecture on the power system stability and control. Today we're going to study about the specifically the swing equation, but before that, it's better to revisit the basic types of stability so that we specify what kind of stability we are going to study, and then there is a homework, computing homework that I will show you. So in power system stability, we are mainly concerned about the electrical power system, and electrical power system has it doesn't only depend upon the electrical parts. It has some other electromechanical phenomena, as well as at the load side, it has some dynamics always which is changing, and the atmosphere. So it's a large scale system. I should repeat, due to the large scale system, the power system, electrical power system, is a highly dynamic and highly nonlinear system. Okay. So when we go and study, we have to study in you can say that we study that in terms of different parts, and then we join them together. Now, concerned about the dynamics, or you can say that the dynamics is all about when the states start changing. So they have their own interdependence on the other parameters. Now this dynamics of the electric, so the dynamics covers states as well as some kind of disturbances. Okay, I will elaborate on this later on, but main concern is the dynamics can be changed due to when there is some change in the load, or the generation itself poses some changes. Okay, even if you change the fuel of the generator, it may have some impact later on the electrical system and so on. The switching, the circuit breaker operations, this is another input to the that may disturb the dynamics of the electrical system. Okay, faults. The major concern is the fault in the power system. For example, we have short circuit and many others, lightning surges, and for example, the controller itself. Okay, since ultimately I will try to show you this thing in terms of the control system, where you have a set point. Okay, and this set point goes to some kind of a controller, whether PLC or a single loop PID controller, okay, or a lead lag controller that we did last time. Okay, and many more. So this controller is ultimately going to do something about switching operations. On off, for example, the simplest is the on off of some kind of switches, breakers. It may be other final control element. Okay, for example, varied voltage, excitation voltage, or something else. Amplifier, for example. Amplifiers, gain maybe, okay, current voltage. And then there is the power system, electrical power system. Then we have some CTs and others, they sense, and then they transmit this value to the concerned controller. So this is a single loop, okay? And we have hundreds of control loops in the overall power system. Now, if something happens with the controller side, for example, the gain, K, which is the gain of controller, even if the gain of controller is changed because of some. So the controller tuning may bring some kind of disturbance to the system. Okay, we will see. Right. And one thing more, that the disturbances are basically affecting this power system. And we have the states here. Okay, so we will have something like, I should say x dot equals to AX plus BU is here. And this thing is basically Y is equals to CX plus DU, right? Where D is somehow this one, U is coming from here, okay? And A basically belongs to this system. B belongs to this system. C belongs to this system. D belongs to, so this is a state space representation of the system. The similar, and I should write it here as well. And this may be in S domain, we can write it like this. For example, 1 plus S upon S squared plus 2S plus 5, for example. So that this can also be a representation of this power system. Okay, so we have to expand and understand how these the external dynamics are happening. Now, interestingly, the dynamics of this system depends upon the speed of occurrence, and the phenomena have, every phenomena has different. I should write every phenomena has, for example, a specific speed range. Okay, for example, lightning. Lightning is very fast phenomena, and for very fast you need quick or fast response. Okay, and up till you have turbine or boiler controls, heavy mechanical systems, heavy mechanical or boiler thermal, you can say that, systems. And basically what these systems are, these are the core energy systems. Core energy system, because electrical energy basically doesn't in large amounts doesn't exist in nature. Okay, it transforms to the other energy form. Basically you have some kind of a turbine or heavy turbine or the boiler systems where we extract energy and high amounts of energy. Okay, and this may be in terms of mechanical form or thermal form, okay, radiation, whatever, and then it goes to the very energy in terms of high speed energy, let's say. My point here is that the phenomena exist here, and the speed of the phenomena ranges from very slow, very heavy mechanical. It has high inertia. I should write high inertia first, high inertial systems. And basically what by this mean is the dynamics is relatively slow or low speed dynamics or phenomena, right? So this power system, to study this, of course, you have to understand it in terms of every aspect. Okay, in terms of speed, like this. So stability is also being so to study this thing. What we need is the type of the models that will help us in conducting this study, right? So Okay, so let's continue. The types of models to study the dynamics. Here I should recall that not all models are accurate, but some models are useful. Okay, so not every model is accurate, but some models are useful. Okay, and according to the required studies, we actually choose between the models, or we actually amend sometimes the models. Okay, sometimes third, second order, first or second order, and now third order, then fourth and fifth, and so on. And even within every model, you can have the equations can be appropriately changed. So the models need to study these dynamics very, okay, and very in detail depending upon the speed of the occurrence. By this, what I mean is the order of model can be changed, and also the detail in equation can also be changed appropriately. So for example, lightning surges, they employ the distributed parameter models, and we use partial differential equations, okay, because this is a large scale distributed network. So we should expect that there should not be a single parameter will be enough. So we have to have some kind of a distributed parameter model, okay. And the second is the slower phenomena, in which this is another important point, that, for example, if you have some kind of a lightning, okay, and you have poles all around here, okay, like this one, for example, okay, we have some kind of this transmission line, some sort of, okay, and then if there is some kind of a lightning on here, so the whole phenomena will be very quick, will be quick phenomena, and the spread or the area will be little bit smaller. Spread is small, but the phenomena is quick. And spread is small. Quick phenomena and spread is small. So in that case, you have to have the small portions throughout the line, in which you are able to capture small areas to capture the phenomena at individual places, for example, okay. You cannot have a big R or L, for example, or some kind of a straight impedance or reactance to represent the whole the complete line of, let's say, 80 kilometers or 10 kilometers or so on. Okay, so the distributed means, try to understand distributed helps us to capture these small changes. Okay, so this is distributed parameter models. They actually help to capture the details of the dynamics at minute, miniature, for example, minute or miniature scale. Okay, distributed way. In a distributed way, the name applies represents very good distributed way. Okay, because a single lump parameter cannot be. But if there comes the next the second. Let me just make a little draw here and here, 1, 2, and 3. Now, if, for example, a single a single, for example, it has a resistance, let's say R1 or Z1. It's better to make it like a Z1, Z2, Z3, and so on, Z10. And a single Z lump is enough to capture the dynamics, overall dynamics. Then it is, and then it means that a single Z will be helpful for me to capture that dynamics which is slow. Okay, and that doesn't die out that easily. Okay, so I have that thing. So this is, and that's why you see the partial differential equation. Same goes for the heat distributed. For example, in the other, if you have a, you can understand, for example, a sheet, metal sheet, and you have some burner here. Okay, you have a flame here, a burner here. So if you are interested in, you can put a temperature sensor on somewhere here to understand. Okay, but that will not be the representation of the whole, but this is so. But if you want to have a temperature profile, you have to divide this into smaller scales, and then you may have a partial differential equation to get this temperature, for example, dt with respect to x and dt with respect to y. So that at every coordinate x and y, you are able to get a temperature profile. Okay, so this for temperature. Similar goes for the high lightning surges, for example, to use the distributed parameter model. So the summary, in summary, within the power system stability, we sometimes have to have the distributed parameter models in terms of partial differential equations that help us to understand and study the dynamics. Then comes the slower phenomena, such as the gradual load or generation changes. Here, the lump parameters are enough. And here you have ordinary differential equation or the lump parameter models like the algebraic equations, they, or even the ODEs, they actually help us the working with the slow dynamics. Okay, so this is the difference between here. You have to have, for example, Z1, Z2, and partial differential, for example, model. And here a single Z lump parameter will be enough. Lump parameters will be enough to study the whole model. So we have to have some different type of models to study the dynamics. Okay, and every model will give us a different different insight, and they are important to study different type of disturbance. So disturbance 1 is studied by this one, and disturbance 2, this is 1, this is disturbance 2, is studied with the help of the lump parameter models. Now let's recall what was the stability definition in the first place. The stability about the power system is simply that your system stay in this step, or it is synchronized. Okay, we have multiple machines and motors, generators. All we need is they should always stay in the synchronism, and they without any disturbance. Okay, so if disturbance occurs, it will try to remain, and they remain in synchronism. This is one thing. And the study of stability against disturbance is categorized. We have some disturbances, against those when we study the stability, and this is called the steady state stability. Another kind of stability is the dynamic, and the third one is the transient. So in steady state stability, it refers when we have a slow disturbance in the system, gradual load, for example, and the system is able to stay in synchronism. This is one type of stability, and it's a very simple synchronous machine model is used here. For example, a generator is used as a constant, simple constant voltage source. Okay, and this kind of stability studies is usually analyzed by the load flow, and where we actually focus on the phase angles and the bus voltages. Okay. Second type is the dynamic stability. for example, this is against the smallest disturbances, okay? Not slow, they are small disturbances. For example, automatic controlled tuning is bad. And in this type of stability, these excitation system and the turbine governing systems are represented along with the synchronous machine by using the linear ordinary differential equations. So the steady state and dynamic stability studies are less extensive in scope and involve one or just a few machines undergo slow changes in the load. So the third, okay, nonlinear differential equations are can also be used for the nonlinear differential equations and algebraic equations of both study cases can be replaced by a set of linear equations and then solved by the linear analysis methods. Solution technique is to examine the stability of the system under incremental variations about the equilibrium point. This is what we did task number 1 to task number 4 here. Okay, it is concerned about this type of stability when we took a 4 ODE model, and then we apply a disturbance in the mechanical torque, and then we try to observe the delta, okay, the variation in delta and 1 or 2 parameters. Transient stability is the large against the large disturbance if the power system faces some sudden large disturbances. For example, a large change in the load, not the gradual, a large or sudden change in the load, which is enough for good enough for loss of generator, switching operation. These type of systems, they require a specific type of analysis. The nonlinear differential equation and algebraic equations don't allow the linearization process in this type of because these phenomena is quick and the effects are sometimes very specific to some places, and we have to have some kind of a direct methods, okay, a different distributed manner, or the iterative process, step-by-step process should be done. We will do some transient stability later on, some examples as well. And the transient stability problems can be subdivided into the first swing, which is based on a simple generator model, and multi-swing, which is based on the effect of generator control system along with the generator model. Okay, so the period under investigation can vary from a fraction of seconds, very quick, over 10 seconds, and multi-swing case. So, but there is one point I would like to highlight here is, in all these stability studies, the main objective is to determine, this is our main objective, is to determine whether or not the rotors of the machines being perturbed return to the constant. So ultimately, these are most of them basically currently they have synchronous machines. Synchronous machines, they can be motors or generators, and they have to have a constant to be in synchronism. They have to have a constant speed of operation. So the speed will vary, but it has to come back to a constant speed. The variation should go. Okay, so this is very important thing. Now, let's continue with the string equation. So in string equation, basically, I think it's better to stop here, and then I will continue with the new topic in the next slide. Thank you.